In this presentation, we're going to talk about how information flows in complex systems and how those information flows contribute or not to the robustness of the system. We'll also talk about how we define robustness in these abstract systems. So what we're going to do, first we're going to consider a little bit. I mean, this is kind of my research focus for a while now. It's been the relationship between network structure and the network's dynamics or its functionality. Um, so this has been performed. Much of this research has been done with Boolean networks, which are a particular type of abstract, complex network, dynamic network that, although are fairly simple, they do demonstrate, much of the behavior you see in more complex systems. We'll also define what we mean by dynamical robustness in these systems. And in doing so, we'll identify something called walls of consistency or constancy, and the dynamic core that emerges when we run these networks, and how dynamic cores and these walls of constancy lead to modularization in the network. And from this, we'll look at the role of non-conserving information loops. So loops where the information is not transformed as such, it is basically stopped. The flow of information is stopped because of the certain information or certain feedback loops in the system. And then we'll give some conclusions on phase space compression and robustness. So what is a Boolean network? We see here a very simple example of a Boolean network with 6 nodes. Each node has a number of inputs. I believe in all of these, each node has 2 inputs. And for each node, we have a rule that tells us what the state of each node will be on the next time step. So each node can only have a state of 0 or 1, hence the name Boolean. And the state of the node, whether it's 0 or 1 in the next time step or the next iteration forward, is dependent on these rules. So we have 2 inputs. So for this node here, we have 4 possible combinations of input. We have 0, 0, 0, 1, 1, 0, and 1, 1, which corresponds to the states of the two neighbors or the 2 inputs coming in. And with those 4 combinations, we have a number of different rules that can be applied here. So if we look at the rule table here, we can see what these different rules might be. So we have 4 inputs, we have 16 different rules, and these are all Boolean, so they're logical expressions which dictate the output based upon these different inputs. And we can see some of them here. We have, the logical names of these types of these rules. So this one actually here is not, and we have contradiction, implication, double implication. Basically, just a simple rule that says, if this is the input, these are the inputs, this is what the output will be. And so for these simple networks, we have, in this case, we have 6 nodes. We could obviously simulate much larger networks. For this particular case, each node has 2 inputs or 2 neighbors. Again, that could be variable for the different nodes, or it could be fixed to a different number for the different nodes. And we have, so the number of rules will depend on the number of neighbors or inputs per each node. If the inputs or neighbors is fixed, then the number of rules that we have available is going to be 2 to the power of 2 to the power of k. And then the number that grows much quicker will be the number of configurations. So the number of configurations for this particular network is simply given by a string that concatenates the value of each node at each time step. So for this particular node, we'd have a string of 6 zeros or ones that define the current state of the system or configuration that completely defines the current state. And if we have 15 nodes, for example, we can see here that we would have 32,768 different configurations that this network could be in. And as you can see, it's to the power of n. So this size of this space grows very, very fast indeed. So here's an example of a Boolean node, a Boolean network being simulated. So the first row here, this gives us our state of each node. So we can see node 0 is on or 1. The next node 1 is off, 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 on, and we kind of get the gist of this line here gives us the full initial condition for this network before it's simulated. Then the next line, we look at each one of these nodes, we look at the neighbors, we look at the inputs to it, and we use the rule for that network, or for that node, sorry, to determine the next step. And all we have here is, as we go down the page, we see how this network evolves over time. And each row gives us the full description of that state as we step forward in time. And you can see with this one very quickly, we've got to seem to have a very interesting recurring pattern. It certainly doesn't look random at all. And what we find with these sorts of networks is, depending on the initial conditions, because the size of the state space, or alternatively phase space, is finite, eventually it will stumble across or it will return to a configuration that it's been to before, and we'll end up with a loop, a cycle. So depending on the rules, depending on the structure of the network, will determine completely what are the different cycles or attractors or endpoints that this network will go to, and how long it takes to get to those endpoints or cycles. So here we have an example here. I believe this is 15 node network. We can see that it's unlike the first one. There are a different number of inputs for them. It isn't a constant 2. And what we have here is a list of the feedback loops that exist in this network. So, really all we're talking about here is, we start at a node, look where it's going to next, see where that node's going to, and find all the loops where, by following this path, we end back to where we began. And here we have the list of those structural feedback loops, I'm going to call them, for this particular network. And on the right-hand side here, we have, actually, this is the dynamic structure. So there's two things going on here. First, we have the structural feedback loops that are kind of hard-coded into this network. We also have, when we simulate this network, we find that depending on initial conditions, it will tend towards one particular pattern or another. And as I said on the previous slide, those patterns tend to be cycles, and the cycles have different periods. So, if it stumbles across a state that then becomes fixed as we move forward, then we call that period 1. It basically hits a constant configuration and stays like that forever. If it oscillates between 2 states forevermore, then we call that period 2. And what we can see here is these are the dynamic attractors that emerge for this particular network given these structural feedback loops. So we can see that this has 3 period 1 attractors. This network can converge to 2 period 2s, and all the way up to a large 1 period 12 attractor, or cycle, where this system, depending on initial conditions, will find itself in a state where it's repeating a pattern of 12 different configurations. And the histogram on the right here is just highlighting or showing the number uh, of attractors with particular periods for this particular network. So as we talked before in previous presentations, the challenge with these networks is that even if we have full knowledge of this system, its initial conditions, its structural feedback loops, there is no way to derive or determine what its dynamic behavior, the dynamic set of attractors will be for this network in advance. We basically have to run it forward and then and run it for all possible initial conditions until we to account for all the possible behaviors that this system or network will display. Another kind of piece of sort of nomenclature is that we talk about, we sometimes refer to these different attractors, like period 1 attractor or period 2 attractor, as the network's function. Um, so in this case, if we added up all the different numbers of attractors here, this would tell us in a sense that this particular network has that many functions it can perform. Each attractor, each end state is suggesting a particular type of function, a particular operational mode for this network. So let's talk a little bit about how we might define robustness in these sorts of systems. Now, there are different combinations of information conserving loops that are active in each different attractor. And what we mean by this is that as we run these systems forward, we find that some of the nodes kind of get fixed in a certain state. They get fixed as a 0 or they get fixed as a 1. And as the system continues to, evolve as time goes forward, those nodes stay fixed as zeros or ones, called frozen. And if you then refer back to the structural feedback loops, what this suggests is that a number of those feedback loops are being kind of cut off. They're not allowing information to flow anymore. The information might go through the first few nodes, get passed on to the next one. But as soon as it gets to one of these frozen nodes, information doesn't pass any further. So essentially, that feedback loop has been cut off. It's no longer playing a role in the ongoing dynamics of this system. The other interesting thing, of course, is that determining those frozen nodes in advance is again essentially impossible. You have to run the system forward. You have to wait till it hits one of these attractors, and then you can see what the frozen nodes might be. And the reason they freeze, it's all of those interactions, all of those interacting feedback loops, non-linear feedback loops, interacting in such a way as to result in this node being frozen. So it's an emergent property of the network. So we have these frozen nodes. We have this. This means that certain feedback loops are getting cut off. That certain information flows now are not continuing to function. And for the different attractors or the different long-term dynamics of these systems, different nodes will be frozen, which is essentially saying different structural feedback loops are being disengaged or turned off, preventing information from flowing. So depending on our starting conditions, the network will evolve to different end states, different functions that have different sets of frozen nodes, and they will have different information feedback loops active or not. And so if we look at some of these attractors, this is just one way to view an attractor. This is a P1 attractor, another P1 attractor, and a P2 attractor. This is saying that after a certain amount of time, depending on the initial conditions, the network will stop changing and it will hit a configuration that it will repeat indefinitely over time. Same for this one, and for the P2, the network will evolve to a state where it's oscillating between two global configurations or states for the system. The branches coming off of this are the states that are, for instance, here are one step away from that endpoint. So if the network was seeded with any of these configurations, it would end up in the P1. And if we step basically further out, so these are just further steps away from that attractor. So any of these points outside of the central point will eventually end up here. So we can see if we started all the way out here, we can track completely deterministically how we go from one state to another, to another, to another, to another, to another, to another, till we hit the period one attractor. And we have the same thing here. And so another way to represent this is called a destination map. And in this particular example, we have 3 attractors given by the different colors. Each square is one of the configurations of the entire network. So remember earlier on, there's a 2 to the n states that this each Boolean network can go into. So this square here represents every configuration of this particular network, and each configuration has been colored, or each point has been colored depending on which attractor the network would finally end up on if you started at this point. So we have 3 attractors, we have 3 colors. We can see we have, the attractors have different sizes. So we can see, here we have an attractor that has only 8 points. So only 8 points to take you to that attractor. We also have, large areas where if you started from any of these states, the system would end up in a particular attractor. And we can also see that this destination map is not carved up in a nice, neat way. You have attractors kind of rather close to each other. If you started here, you would go to one attractor. If you started here, just this is a kind of a 1-bit difference in the initial conditions. You would end up here. If you started in this state, you would end up in in a different attractor again. So the way in which these attractors or these functions are distributed over the state space of this network is complex in itself. We don't just get a nice carving up of state space to say, if you start here, you go to this attractor, you start here, you go to this attractor. They can be intimately mingled. So these are areas where we're particularly interesting, because if you're in one of those areas where the phase space shows the attractors are very closely intermingled with each other, then small perturbations will be able to push you from one attractor into another. So bear in mind that that's essentially also saying a small perturbation can change the overall global behavior of the system. With one gentle little nudge in the right direction, you can completely qualitatively change the behavior of the network. So given that over time, we generally want to see our networks fairly stable, knowing that there are regions where it can be readily nudged into a completely different mode of operation is of interest. So this diagram kind of comes from this in a slightly different way. So this is showing us how these emergent networks, these dynamic Boolean networks, will evolve in such a way as to almost carve themselves up into separate sub networks. And this is a critical process. If there wasn't this notion of modularity, then the system would almost be chaotic. It would explore every possible state. You could think of it as having one gigantic chaotic attractor, and that would be it. And by chaotic, I just mean it would jump through every state of the system essentially randomly. Yes, it would be a cycle, because eventually, this is a finite system, so eventually it would return to the same spot. But it would be exploring, all of the states of the system and have no real sort of coherence to it. So what we find in these networks, what really happens is, so we start off with our network, we've given them all the rules. As we simulate this network, we find that there are certain nodes, depending on our starting condition, that become frozen. So as we talked about earlier, these stop information from flowing um, around the network. They limit the dynamics of the network. They constrain the possibilities of the network by them being there. But as we kind of see here, is that's kind of a good thing, because this then enables the network to limit the space in which it explores and actually have a particular type of function, meet a particular purpose. Obviously, purpose in this case is a little bit tricky to assign, but what we're saying is that it's no longer a kind of semi quasi chaotic system. It's evolved into a state where there are a number of independent nodes, a number of independent modules that act independently of the others, and overall it constrains the behavior of the system, or constrains the system to not explore the full state space, which then gives it, a particular function. Um, you can imagine, if you have a system that is capable of doing anything, anytime, anywhere, what use is that to you? I mean, it has no focus. It has, you need some kind of limitations to define the boundaries of a system, to define the focus, to define a a function, something that it actually does. So this chart shows this here. So we're going from the full network. We're seeing the emergence of frozen nodes, which cut off a number of the feedback loops, which leads to a number of independent modules that do a more limited set of computations. And we also have, these additional, the ones that we've removed. So, what role do these play? Um, you could argue that, these frozen nodes do nothing at all. They're taking away from the dynamics of the system, but at the same time as they're taking away, they're also constraining the behavior of the network in a meaningful way, so that actually does something. So the language you've used from going from here to here is this is the full form of the network, but this is known as the reduced form. So this is a simplified version of the network. It could also be called like the dynamic core, because we still have feedback loops going here. We still have information passing around, moving around these modules, but a number of feedback loops have been disabled because of that. And kind of to re-emphasize the point, we can't go from here to here using nice traditional analytical math. We basically have to run this system forward, identify the different frozen nodes, identify the disabled feedback loops, identify the modules that have emerged from the system. And we have to do that for all initial conditions, because for most of these systems, there will be multiple solutions, depending on where we start. So another particular example of this. Here we have a network with 10 nodes. Here are the rules here for the 10 nodes, and here are the inputs. So if we look at input 9, according to this, 7 and 8 are both inputs into 9. We see that there. And here is the rule for how we evolve that node depending on what the inputs are. So if we evolve this particular system forward, let's say we do it we do it in a way that we end up or we pick our initial conditions that we end up on this particular attractor. So this is a period 4 attractor. If we then identify the nodes that have become frozen, i.e. fixed at 0 or 1, and remove those, we end up with this network. So this network, one way to think of this is network is functionally equivalent to this network. this network has 2 period 4s, hit this one, and this network also has 2 period 4s, this one and the one hidden here. So in that sense, they both have the same period for attractors. So in a sense, they're functionally equivalent. These two networks do the same thing. But this one does it with less resources. It's we have what do we got? We got only 5 nodes here, and 1, 2, 3, 4, 5, 6, 7 connections. The ones with circles around it are connected to themselves. So this is interesting. I mean, is it reasonable to say for a real world network, can we look at its structural properties? Can we then simulate it and use its dynamic properties to uncover a dynamic core, which would provide the same function, and then throw away everything else? I mean, why do we need all these other nodes in here? What do they give us? They're not contributing to the function. We can create a network with the same function using just the dynamic core. So why spend time and effort maintaining a network that's considerably larger? I mean, it's twice the size, the original network here, as compared to its dynamic core, which is, as I said, functionally equivalent. So it looks like you can, if you have to monitor the system's behavior forward and make these identifications afterwards, but it looks like you should be able to look at a dynamic system and identify the resources that contribute to its function and the ones that don't, and throw away the ones that don't. But as we'll see as we go on, the story is far more complicated than that. So here is, we haven't talked about what we mean by robustness yet, but this is where we need to talk about what we mean by robustness. So robustness in the Boolean networks we're looking at here refers to, if I take any given state in the network, in the state space, and I change one of the states in there, I flip it. So I say so I've got one particular state that represents the state of each node. I change the state of one of those nodes, and then I evolve the system forward from there and see whether it stays in the same attractor. If it stays in the same attractor, its long-term behavior is unaffected, I say that the system is, or that state is robust to a single node changing single node perturbation. So an external entity comes in, changes the system, changes that one node state, but it has no impact. The system continues to evolve towards that same attractor. So again, it's robust to that one change. But what you often see is you make one of those changes, and then the system's dynamics changes completely, and the system moves into a different attractor. So for that particular state where we make one change on one particular node that changes the long-term behavior of the network, or the performance, or the function, or the mode of operation, this is now sensitive to external perturbations. So what we do to define robustness for the entire system is we take every single step. We run this millions of times, and what we essentially do is we take every single possible starting condition, see what attractor it runs towards, make a random change to one of the nodes in there, which would mimic an external perturbation on the system, run that forward again, and see which attractor it then went to. And the robustness that we then calculate is the percentage of one node changes that we can make that would still lead to the same attractor that we were in before. So if robustness is really, really low, we're basically saying that any perturbation, any small change from the outside is going to affect the long-term dynamics of this system. It's completely at the beck and call of any external event that will make a single node change its state in the system. Whereas if the robustness is 1, then basically there's no change you can make from the outside that would cause the behavior of the system to change in the longer term. So obviously, if you have a state space which only has one attractor, this only has one function. There's no optional other attractors that this system could go into. So it's a 1. But what we find is most systems have multiple attractors, and most of them are not completely stable to external changes. And so what we have on this plot here is it shows us what is the robustness of the network that we start with, and then what is the robustness of the network that we get when we take away the frozen nodes. We identify the dynamic core of that system, which has the same function, but we calculate its robustness. And so, even for the network that's not that we start with originally, its robustness is rarely going to be 100% or 1. It's going to have multiple attractors, and you make changes, and it will change to different attractors, be pushed into different attractors. So what we have on the plot here, we have the unreduced robustness, which is the robustness of the network before we take away the frozen nodes, the non-conserving information loops, before we identify what the dynamic core is. And then we calculate what the robustness is for the reduced network, i.e. the dynamic core, the one with all those frozen nodes removed, all of those non-conserving information loops removed from the system. And so the solid diagonal line here is showing us where the reduced robustness and the unreduced robustness would be the same. And the red line here is showing us what is the robustness of the fact that it's below the blue line is showing us that in just about every single case, the robustness of the dynamic core, the reduced network, is less than the original network we started with. So at the very least, we can say, well, they may be functionally equivalent, these two networks, the robustness network and the reduced and the unreduced networks are functionally equivalent, but the reduced network is less robust to external changes. And the other, you can see, we're basically running this on millions of random networks, finding the robustness of the original network, identifying the dynamic core, calculating the robustness of there, and then averaging that over thousands of different runs. And so there's a bit more information on here that tells us about how many data points there are that go into the calculations of the red line. So, for example, if we're looking at around 80% for the unreduced robustness, there were about 5,000 networks that were used to find that point, to find that average. And we can see, most of the networks that when we create them have a robustness, above 60–70%. So this is an interesting result. We're showing that the functionally equivalent simplified network is less robust than the full network itself. And here's another plot of this. This is really just the previous plot, but showing the actual raw data. And what was interesting for this particular study was you start seeing kind of these different rays coming out through here, and they're basically they correspond to the number of frozen nodes in those networks. So if there are no frozen nodes, that's generally typified by having a single large attractor, and the reduced and unreduced robustness is the same because we're not taking any nodes away. The original network is the dynamic core, and vice versa. If if one of the nodes becomes frozen, then we have a dynamic core which has one less node than the original network. And we have that pattern here, and so on as we go through reducing or identifying networks that have more and more frozen nodes, which also means smaller and smaller dynamic cores. So as we go through this list, we're looking at networks that are functionally equivalent, but the dynamic core is getting smaller and smaller. And we can just see more gaps in it as it's harder to find examples of those sorts of networks. But again, what we're showing here is that the robustness of the dynamic core, the simplified functionally equivalent network, is less than the original network. And here's one way to see that kind of visually. So here on the left-hand side, we have the phase space or the state space of the original network. So this is again showing us for every possible network state, global state, which attractor that point will eventually evolve into or emerge into. So we can see on here, we have quite a lot of purple kind of gathered in this region. And there's big areas of green, but then we also have some interesting areas where the attractors are kind of intermingled, that a small push in one direction or another would be enough to qualitatively change the behavior of the network. If that happened here, if we had a small nudge here, nothing would happen. The system would stay in the same attractor that it was currently in, i.e. its mode of operation would change. It would be functioning in the same way. So what we have on the reduced network, though, the dynamic core, we see we have the colors here correspond to the same the same attractors, the same functions that we had in the unreduced network. But we can see, first of all, the main thing is this phase space. This isn't actually to scale, but this phase space is much smaller. We have far less points, far less possible states in the reduced network. The number of nodes are smaller, which means the size of state space is exponentially smaller. So what we can see here is, we have a little bit more intermingling here, but the chances of targeting a state, intervening with a change, the chances of us doing that and it leading to qualitatively different behavior in the network is greater. So at the very least, we can see here that the dynamic core has a much smaller phase space, so is more susceptible to external changes than the unreduced phase space. So if nothing else, these non-conserving structural information loops are increasing the size of phase space and making the system less susceptible to external perturbations. So just to kind of summarize some of what we've learned here, what happens when we run Boolean networks forward is that rather than allowing all of those feedback loops that were there at the beginning to continue to determine the future state of the system, it emerges into a state where certain feedback loops are turned off, and this kind of naturally reduces the complexity of the dynamics of the system and gives it more focus. And this happens through modularization of the network. This isn't a system that's been designed to be modular. It's the modularization is an emergent property of the network itself. And Prigogine, which is a very well-known nonlinear dynamicist, talked about self-organization requiring a container, self-contained organization. And this is kind of a critical idea in complexity, is that the complexity has to be constrained to some extent. Otherwise, you won't get self-organization. You just end up with a chaotic mess. So the emergence of modularity, the emergence of these walls of constancy are essential for self-organization to occur. Without that, we have chaos essentially. And in this particular system, these non-conserving information loops are the ones that provide the function of a container. They are limiting the dynamics of the system. They emerge, through emergent processes, they are limiting the dynamics of the system, providing a container in which a level of organization which is constrained, not chaotic, it emerges that gives the network a particular function rather than just randomness. And in a very simplistic way, the nodes that are removed when we identify the dynamic core, if nothing else, what they do is they double the size of phase space. So for if it's 2 to the power of n, where n is the number of nodes, so every node extra you have that's connected, you are doubling the size of space. So you're doubling the size of the space that for which external perturbations could be targeting. So the chances of targeting a point which is particularly sensitive to perturbations which change the qualitative behavior of the system is much lower if it's a much bigger network, a much bigger phase space that is functionally equivalent. So if nothing else, the size of phase space being doubled for each node, it contributes to the robustness of the full network as opposed to the dynamic core reduced network. And as another way of just saying this is, the inclusion of frozen nodes at least increases the volume of space. So there's two things here. I mean, it's they can't be untangled in a nice, easy way. The emergence of the frozen nodes, just the existence of them results in a larger phase space, which is less sensitive to external perturbations. But at the same time, they also lead to modularization, which constrains the macroscopic dynamics so that the system itself has a well-defined function rather than behaving chaotically. So, both of these characteristics of the network are essential. And it's these frozen nodes, these non-conserving information feedback loops which provide that. They are critical to the function of the network. And what I've said already, by having a larger phase space, the chances of hitting an area that will lead to qualitatively different behavior in the system is significantly reduced. But this doesn't just mean you can arbitrarily throw resources in there with the idea that they will absorb the energy from an external perturbation or external attack, because they play the dual role of also modularization and simplifying the information processing and that leads directly to the function. So these things can't be separated. So non-conserving information loops do not necessarily act as impenetrable barriers. I mean, they're stopping information flowing around that particular loop, but by doing that, it's supporting not only modularization, but also improved robustness of the resulting system. They play an important information distribution control role. So, this idea that information should be free and should just go everywhere, and the system should have access to all the information it could possibly have, and that would always lead to better understanding or better functioning. In these systems, that clearly is not the case. The distribution of information needs to be constrained. And it's through that constraining that the function of the system emerges. So versatility comes at the cost of reduced dynamical robustness. So what we're kind of saying here is if we focus for a moment on the functionally equivalent dynamic core, it's going to be much easier for us to change the qualitative behavior of that system, i.e. nudge it into a different attractor. It's much easier for us to do that. It doesn't take so much work to move it from one state to the next state because it's got a smaller phase space. There's less resources. Um, it's easier for us to make changes to that system in a way that function qualitatively changes its behavior. But at the same time, it also means it's more sensitive to unwarranted external changes, uninvited perturbations from the outside. So it's you get a system that's much easier to change, but it's also more easy to change for the wrong reasons. So it's kind of a two sides of the same coin. More flexibility doesn't necessarily mean a better system. You have more flexibility, but there's a big cost for that increased flexibility, which is it's also easier for somebody else to not nudge that system into a different state. So there's a trade-off between flexibility and robustness that we've talked about quite a lot. What the phase-space representation also shows us is about this idea of adjacent possibles. The idea of an adjacent possible is if we take any particular configuration of the system, what's a reasonable next step for this system? What's a reasonable future for this system? Could we change it in certain ways that are easier than others? And if we stay with the idea of attractors, then if we want to move the system from one attractor to another, is that equally easy for all of the possible attractors, or are some attractors easier to get into than others? And the concept of adjacent possibles is dealing with that. So if your system's in a particular state, there will be certain attractors that are more easily reachable than others, and understanding which ones are very hard to get to and which ones are very easy to get to helps you understand how you might evolve the system forward, or how you might make a change to respond quickly to an undesired external perturbation that's trying to push the system in a different direction. So I think this is what I've always found interesting about this is that it leads to a conclusion which seems to goes against some of what's kind of popular these days, which is information should be free, information should be everywhere. There should be, the more information we have, the better the outcome will always be. And for these dynamic Boolean networks, I think it's very clear that it's the limiting of information flow that leads to organization. It's the limiting of information that leads to function. Everything goes does not lead to well-defined function. Now, can you determine which information needs to be flowing at the right times? That's a big question. But clearly, just allowing all information to be available everywhere, always, is not going to lead to coherent, robust, well-functioning systems. But again, there's obviously challenges up front to design a system in a certain way where the right kind of information is flowing and achieving the right type of function in the first place.